Hello, my name is Abhishek and this is Digital Assignment 1 given by Sir Dhanbal R. In this assignment, we have to choose one microprocessor and answer 10 questions about it. My register number is 18BEC0909, my serial number is 59 and my slot is C1. The first question is to draw a block diagram of the microprocessor. Given below is the block diagram of the microprocessor. The second part of the question is to draw the internal diagram of each and every block. So, Cortex A73 processor consists of elements such as decode, rename, branch prediction, branch, DE register file, dispatch, issue, advanced neon floating point, which we will discuss later in this video, arithmetic logic unit, write back register, AGOs, and 34 kilobytes or 64 kilobytes of D cache. The second question is to provide the instruction set of the microprocessing element. So here we think instruction set of the microprocessing element, and some of the instructions are ADC, ADD, and BIC. All the instructions are given with the action for the form. So these are all the instructions. Microprocessor. The next question is to explain microprocessing element architecture. The Cortex A73 processor implements an ARM V8A architecture with advanced SIMD support and optional ARM V8 cryptographic extension. The ARM V8A architecture that is implemented in the Cortex A73 processor includes support for both ARC32 and ARC64 execution states, support for all exception levels EL0, EL1, EL2, and EL3 in each execution state. ARM V8 debug architecture, GIC v4 interface, AMBA 4ACE, bus architecture, ATM v4 architecture, instruction traceability, the A32 instruction set previously called as ARM instruction set, the T32 instruction set previously called the thumb instruction set, the A64 instruction set. The Cortex A73 processor supports the following features: floating point and advanced SIMD support for integer and floating point vector operations. The advanced SIMD architecture, its associative implementations and supporting software is also referred as Neon technology, which was already seen in the block diagram given above. The next question is to correlate microprocessing element architecture with architectures discussed in Module 1 and Module 2. ARM architectures usually use hardware architectures, which has been discussed in Module 1. In ARM, we usually have hardware bus architecture, which means instruction and data accesses can happen at the same time. However, memory space is unified, which means both instruction and data share the same memory space. The next question is to elaborate register organization of microprocessing element. In ARM architecture, we usually have 31 general purpose plus 2 dedicated registers, each 64-bit wide. 2 dedicated registers are one of the dedicated registers is the stack pointer SP register, which holds pointer to the bottom of the stack. It is the preferred register while accessing the stack. This register is a 16-bit aligned register. The next register is scalar, FP, and SIMD registers. These are separate set of 32 registers, each 128-bit wide, architecturally named as V0 to V31. These are used by scalar, floating point, and SIMD instructions. The instruction syntax uses qualified register names: BN for byte, HN for half word, SN for single word, DN for double word, GN for whole word. In the next question, we have to explain the type of algorithm used for signed and signed calculations, such as addition, multiplication, or division. The arc64 specifies that division by 0 produces 0, then we can just use c equals to 0 and using that in B and C gives 0. Just like the original division instruction, however, at least Cortex A53, A72 and A73 have very fast dividers, so a compiler probably should follow replacing division by multiplication with the reciprocal of for these CPUs. Still, if there is a CPU with slow division instructions with division by 0 produces 0, you can apply these considerations. In the next question, we have to find out the control logic type used and correlate its performance with the type of control unit in module 3 in the COA syllabus. The floating point used in this microprocessor is neon floating point unit, which has been discussed before in this video. The next question is to explain the memory management system in the processing element selected. To list its addressing capabilities, memory mapping technique followed. Find the advantage of memory design and management techniques over the concepts given in Module 4 in COA syllabus. The L1 memory system consists of separate instruction and data cache. The size of the instruction cache is 64 KB. The size of the data cache is configurable either to 64 KB or 64 or 32 KB. The L1 instruction memory system has the following key features: virtual indexed, physical tagged, a 4-way set associative instruction cache. These are the features of the L1 instruction memory set. In the L1 instruction memory system, aliases are not handled in the hardware. Fixed cache line length of 64 bytes, pseudo-random cache replacement policy, and some more features of the L1 cache system are given below. The implementation specific features of the instruction and data caches include: at reset, the instruction and data caches are disabled. Both caches are automatically invalidated immediately after reset. We can enable or disable each L1 instruction or data caches independently, but you cannot disable the L2 unified cache and the L1 caches independently because they are controlled by the same enable bits. Cache lockdown is not supported in this processor. On a cache miss, data for the cache landfill is requested in crucial word first order. The next question is to elaborate the pipeline and parallel processing capabilities of the unit and hazard management technique. Pipeline is a mechanism used by a RISC processor to execute instruction at an increased speed. This pipeline mechanism speeds up execution by fetching the next instruction while other instructions are being decoded and executed. During the execution of an instruction, the processor fetches an instruction, it means loads an instruction at form memory, an instruction, and writes back it to the register. The ARM7 processor uses a 3-step pipelining process, which is called fetch, decode, and execute. The image for the pipelining is given below. The hazard management techniques used in this CPU are pipeline bubbling. Hazards are the problem with the instruction pipelining in CPU microarchitectures where the next instruction cannot execute in the following clock cycle and potentially lead to incorrect computation results. 3 common types of hazards are data hazards, structural hazards, and control hazards. Pipeline bubbling. The pipeline, also termed as pipeline break or pipeline stall, is a method to preclude data, structural, and branch hazards. As instructions are fetched, control logic determines whether the hazard could or will occur. If this is true, then the control logic inserts no operation into the pipeline. This helps in eliminating potential hazards. Further explanation of pipeline modeling is given below, given on the screen. The next question is to find whether processor level parallelism is available in the element selected, and to illustrate cache coherence and protocol used for handling memory hit or miss. Parallel level parallelism is not supported in this microprocessor. Disabling cache is the simplest mechanism but may cause significant CPU performance. To get the highest performance, processors are pipelined to run at higher frequency and to run from caches which offer very low latency. Caching of data is accessed multiple times increases performance significantly and reduces DRAM access and power. Marking data as non-cached could impact performance and power. And these further explanation of this is given below. Now I will be showing one of the flowcharts in raw.i.